magnitude of the work done by the friction. That's it. Now, of course, to know the work done by the friction, you need to know how to find the force of friction. In many problems, it's very simple. In some problems, it's not that obvious, but we will do it. We'll do them. Right? There it is. That's your minus there. All right. So that's the work energy theorem, guys. So now the change of energy is not zero, right? It's not that the energy initial is equal to energy final. Now the energy is changing due to an external force, which can be friction. You are traveling at 65 miles per hour with some kinetic energy, of course. You suddenly skid to stop because of congestion, because of traffic. What is the kinetic energy your car once had? It's all internal energy in the tires? No. Some of it has transformed to internal energy, and some of it has been transferred away by mechanical way. It's all been transferred from the car by various mechanisms. So when you skid and your cars are going to stop, some of the energy goes into internal energy, heat, for example. Some of it is transferred away by mechanical waves. All right, sound, for example. Notice how they don't mention friction in here. The problem doesn't say friction, right? This can happen in ice. So, okay, so here it is. That's a problem that you put. Actually, I make it more complicated. So I'm going to add an incline plane. Do we have time? Yeah, we have time. And in some way, it's good because we're going to review incline planes as well. So actually, this is good because you have an exam on this today, right? So we're going to be reviewing friction and forces with this. Okay, so you have a 6 kilogram block that is initially at rest and is pulled to the right along the horizontal side by a constant horizontal force of magnitude 12 newtons. Find the speed of the block after it has moved 3 meters if there is friction of 0.15. Hey, you can do the problem without energy because you know the mass, you know mu, you can find the, I mean, it's giving you the free body diagram there, right? But let's do it with energy. It's asking you to find the speed. If you want to do it with forces, you have to find the acceleration and then do kinematics. There are extra steps. So how will you do that problem with energy? So take a look at it. I'm going to erase a whiteboard. And then let's analyze that system there. So let's stop sharing. You have a block on a horizontal surface with friction, no? And the block is being pulled. It has 6 kilograms. The force is 12 newtons. Mu is 0.15. Find the speed after moving 3 meters. So final. Okay. We're gonna use the work energy theory. That it says that the work done by external forces is equal to the change on kinetic plus the change on potential. And also internal, but in this case, we just system, we just worry about this. Obviously, in this system, the potential energy is just 0 joules. So we don't worry about it. Your position A is this. Position B is this. So in the free body diagram, sorry guys. The free body diagram that they give you, they already show you the friction, right? So what's Fk? You remember for today is mu k times the normal force. Now, because there are no other forces acting, the normal force, remember, this is the weight of the mass, the weight, 6 times 9.8, so 6 gravity, and the normal force is like that. So the kinetic friction will be 6 times 9.8 times 0.15. D98 times 9. $8.82. Yeah. No, 8.8 newtons. So, and this is 6.0, so but there is a force that is making the body move. So the net external force, F net, the magnitude will be 12 minus 8.8, which will be 3.2. 3.2. So the work done by the external force is 3.2 times 3 meters. Force and distance. I told you that last class, right? In many situations, you're gonna use that, like magnitude-wise, which is 9.6 joules. But that's equal to the change of kinetic energy. It's at rest here. So that change 9.6 will be kinetic energy final minus kinetic energy initial, which is 0. Kinetic energy final is 1/2 of the mass times velocity final squared. That's it. $1.8. Which you can round to 2.0 if you want. There you are. Hmm? Look how many things get, right? Forces, friction, war, energy. Right? That's the thing about physics. It builds from previous concepts. A mass going towards a spring that has it's attached there. And the mass has some velocity of 1.2 meters per second and is of 0.8 kilograms. And this velocity is calling at this point A is 1.2 meters per second to the right. And the spring has a spring constant of 50 newtons. Assume no friction. Calculate the maximum compression of the spring after collision. So the thing about this problem is that because there is no friction, we can assume that the block will reach the spring with the same velocity. If there was friction, you can't assume that because there will be some energy lost. So you have to take into consideration that. But pretty much what's telling you is that the block will reach a position here. And the spring will be compressed. So you want to find that value. To find the maximum compression, this is when the mass stops. Just like we did in the problem vertically. So that's easy. Energy on A, this is position B. Energy on A is equal to energy on B because there are no other forces acting on the system. Energy on A is just 1/2 of the mass times 1.2 squared. That's equal to when the block stops, there is no more kinetic, but there is what? Potential elastic. 1/2 K x squared. Very easy, right? You're just making one equal to the other. This cancels, this cancels. We have 0.8. That divided by 50. If I take the square root, I get 0.15. Passing meters. In centimeters will be 15 centimeters. That's the maximum compression of the spring. Okay. I want to change the problem from the slides. You know why? In the second part, they tell you that now the speed is that when the block reaches. And I guess you can do it like that. But it will be the same actually. I will just make it longer. I mean, if I tell you that it's in here, and now there is some friction, you will have to find the energy here, which is kinetic again, and then it's losing energy due to friction until it stops again. So it will be the same. But now we have to worry about the work done by friction. That will be the difference. So let's do what it says there actually, and then I will show you what happens if the block is actually at this position. So the next part will be this. The idea is the same, so there's not much difference. Now we're gonna add friction though. Friction is given by mu equal to 0.5. Yes. So now you have the same situation here, but now the mass is spring. But now the mass is here. And the speed, or the velocity is, again, at that point. So it's like saying that now there is friction below the spring. K equals to 0.5. And the constant of the spring is the same in 15 newtons per meter. So what will be the maximum again? The maximum compression. So position A is sort of the same as that. Position B, it will be also this. But now, due to friction, the change on kinetic energy is equal to the work done by friction. Now you're probably thinking, but the change of kinetic energy will be negative. Feynman said, look, to apply that, you can say yes, minus the work done by the friction. Or you can say energy initial minus energy final equals to the work done by friction. So you get a positive here and positive there. The initial energy is the kinetic energy. So the same. The final energy is also that. So far, so good. They are not equal anymore, so that's okay. That's equal to what though? The work done by friction. Okay. How do I find the work done by friction? I need to know the force done by friction. So that's the weight. And the friction will act across X max. However long it compresses, that's the length. The block will move while the friction is acting. That's why I say it's different if it was that situation. In this situation here, the length will be all this. You will need to know this length. How far the mass is from the spring. Okay. So here, if you want to write an equation, will be mg mu sub k, normal times friction times coefficient times x. You have all these values and you get a quadratic equation. Let's take a look. Mass times gravity times 0.5. So that 1.2 square is 1.15. So 1.15 50x squared. Right, so let's finish in here. So that quadratic equation becomes this: 50x squared plus 7.84x minus 1. Again, we have to use a positive solution. Minus b plus or minus b squared minus 4a times c, but that's positive, so plus 200 times 1.15. 30 divided by 100. All right, so we're gonna have to take the positive solution most likely. Yep, that's 17 minus 7.84 divided by 100, 0.09. Which is equal to 9 centimeters. Makes sense. Because of friction is 6 centimeters less. All right. So in here in the book, they show you a whole bunch of variables first. But it's better, I think, if you do it like that, so you can see what's happening. Okay. So we have done a situation with springs, friction, non-friction. We did a circular motion situation. Now let's do situations where we have angles. Let's do an inclined plane, and then if we have time, I want to go over a situation that is here in the book. All right. So let's see if we can do this in 25 minutes, and then you guys can start with the exam. Let's see. You will see how much more simple it is to do problems with energy. No. Let's put here example. You have an inclined plane. No friction here, but friction on the horizontal. So I'm gonna do it like the angle is 30 degrees. You have a mass M that is gonna slide through this non-frictionless or frictionless incline, and then it's gonna stop here. The length, let's make it 5 meters. First of all, I want you to find the speed here. And then I want you to find the coefficient of kinetic friction. What's mu k? For that to happen. The information that we don't have yet is the length of the ramp. So let's say that the length of the ramp is of, so all this length is of 40 meters. That's all thing. We'll see. Let's make this M10. Okay. So part A, we're gonna find V1. Part B, we're gonna find mu. With forces and kinematics, you will have quite some time in this problem because you have to find energy sign and you have to find the force and then the friction there. So to find V1, we can do it almost immediately. There are 3 positions of interest. There is position A, initial position, the intermediate position, and the final position C. So actually we say that BC is equal to 0. Right? So we want BB. B. Yeah. So on the ramp, the system is isolated. It's only gravity acting on the body. So on the ramp, the change of energy is equal to 0 joules. Therefore, energy at A is equal to energy at B. Now, what's energy at A? The mass of the body times the gravity times h, which is this. You don't know. And what's the energy at B? 1/2 the mass of the body times the velocity at b squared. So the mass cancels, but we don't have h. But wait a second. I have the angle and I have the hypotenuse. So the value of h is 30, like 2, like 1, like √3. This is 15 meters. So the value of h is 15. So the value of BB will be the square root of 2 times 9.8 times 50. That's pretty easy, right? Keep in mind how it's the same as if you were dropping it. That's because there's no friction, so you can do that. 17 meters per second. So that's it. How about mu k? Horizontally, is not isolated anymore. It's a non-isolated system. There are external forces acting on the body. So for the horizontal, there is friction. So the change of kinetic energy is horizontal, right? Is equal to minus the work done by friction, or kinetic energy initial minus kinetic energy final is equal to the work done by friction. This is zero, right? What's kinetic energy initial? That. So 1/2 of the mass of the body times the velocity on v squared, that's equal to what? The work done by friction. Okay. So what's the work done by friction? If we do the free body diagram on the mass on the horizontal, we have mg, no other forces, just the normal, and there is mu. So it will be as mg, which is the normal, times mu k times the distance 10 meters. Perfect. So we didn't need the mass of the body. The mass gets cancelled here. The velocity at v squared is equal to 2 times 9.8 times mu k times 10. But I have velocity v squared. Velocity v squared is 17 squared, right? So 17 squared equals to 2 times 9.8 mu k. Yep, that's what we have. We get a high mu k of 1.47. That's mu. You can do the problem in a more efficient and a more simplistic way by using energy considerations. Right? A block falling through the plane and then reaching a. So combining both, you see, you can do that as well. Right? And then there's a problem here in the book